Here on in AP Physics 1. This video is going to focus on moment of inertia. So remember, we keep bringing up this idea of linear to rotational equivalent. So there's something that is similar linearly that is similar rotationally. Okay, and so one thing to note, right, you're going to see this kind of phrase here, rolling without slipping, a lot soon. And you can see the diagram here. It just says, like, basically as we go through it. So wheels and objects can rotate as well as move in a linear direction. And so what happens is that combination of the two motions, the rotating motion, right, and the linear motion, okay, produces this picture here. But this is our key thing right here. It just tells us that the center of mass is just going to simply move at V equals R omega. Okay, and it's going to be very important when we do that, when we talk about energy, which is going to allow us to substitute some things in. But let's talk about moment of inertia. So again, anytime an object wants to move, it's going to try to resist it, right? In linearly, that was our Newton's first law, or simply the law of inertia. So recall that the physical quantity associated with inertia, right, is an object's mass. So the bigger the mass, the more it's going to resist the motion. The smaller the mass, the least it's going to resist that motion. And that's how things begin to move. Well, guess what? There's a rotational equivalent too. So the moment of inertia is going to determine how easy or hard it is to change an object's rotation. So mass, linear, moment of inertia is going to be our rotation piece. So what we say is an object with a high moment of inertia is difficult to start or stop rotating. The moment of inertia essentially plays the same role as mass does for linear motion. So the moment of inertia is going to depend on two things. One, it's going to depend on the mass of the object. Okay. The second thing it's going to depend on is the radius of the object. And what that does is it leads to kind of like this distribution, right? So the further the mass is distributed to the away from the axis of rotation, the harder it is to really rotate. So in general, the equation for moment of inertia is going to be nmr squared. Okay, if it's just a point, you don't see it over here, but if it is just a point, like an object on something, right, that's going to be just our basic mr squared. Right, so mass times where it's located squared. So this would be when we do angular momentum. If something is sitting, if you drop something on let's say a record player, it's going to slow down, and you're going to have to find the total moment of inertia for that system to include that object. Okay. Now the easy way to look at it is notice this n value, right? So the object with the greater n value, right, this coefficient is the one that will have the highest inertia, right? So the one that's going to resist that motion most. And so typically, here's some common moments of inertia. So for AP Physics, the three, right? So you have to, here in Physics 1, you have to worry about these three up here, and then the one down here at the bottom. Okay, so the cylinder or disc, or it could be a hockey puck. The hoop about the symmetry of axis. So this would be like just an embroidery hoop rolling down an incline. A solid sphere would be like one of the lab spheres. And then a thin spherical shell would be like a basketball. Okay. Sometimes they do throw this one in on you, right? So if I had a rod spinning about its axis, it was in the middle. Not so much here in Physics 1, but in Physics C, they like to do that. And so, again, you're looking to rank these based on that n value. So, like, for example, the hoop, n equals 1. So that would be the one that resists the motion the most. Of the four that I circled, that would be the first one. That would be the hardest. The second one would then be the hollow sphere, right? So this would be number 2, because the 2/3 is the next biggest fraction. Then you would have the hockey puck would be number 3, and then number 4 would be the solid sphere. Okay, so very commonly they like ranking tasks here. So here, let's look at an example problem that has nothing to do with calculating, but has to do with ranking these by who's going to finish first. Okay. So you got these 4 objects placed. Note that they're not this. They don't really have the same mass. Okay, so you have object C is 2 kilograms as opposed to like object 1, which is also a solid sphere, which is 1 kilogram. They do give you the moments of inertia for each one, right? So it says a solid sphere is 2/5, a hollow sphere is 2/3 mr squared, and the hoop is mr squared. So what we need to do is we need to figure out, right? Once I factor in that mass, what does our fraction become? And so they tell you that they all have the same radius, okay? And so let's look at A, right? So A is a solid sphere, so that's going to be 2/5 mr squared, but we're not going to worry about R because for all 4 of them, R is the same. So I have 2/5 times 1, which gives me essentially a factor of 2/5. Now let's look at B. Okay, so B is a hollow sphere, and they tell us that the hollow sphere is 2/3 mr squared. Again, we're not going to worry about the R, and so we're going to say 2/3 times 1, which gives us a factor of 2/3, right? So now if I'm ranking these here, B is going to be hardest, okay? If we're looking at this ranking from fastest, the shortest time down the ramp, so we're looking for the one that will have the lowest. So the fastest will be our lowest value. Okay. Now we would have C. So C is going to be 2/5 mr squared. Again, we're not going to worry about R, but this is now a 2 kilogram object. So now we have a value of, or a factor of 4/5. All right. And now we have the hoop. All right, and the hoop is mr squared. Again, not factoring in that, so we're just looking at the mass, so it has a factor of 1. So now let's rank these. So note that we have a bunch of fractions. So the fastest one going down the incline would be the one with the smallest fraction, so that'd be 2/5, right? And why? Because it's going to resist the change in motion more, or excuse me, not more, but least. Then we have B, okay, because B is 2/3. Which is 0.667. And then we have C. Oh, look at this. It's going to be A, B, C, D. So all the time, if you have a race between objects, the hoop will always finish last. Okay. So something solid will finish first. Okay. Because, and again, remember, it's where the mass is distributed from the axis of rotation. So in a hoop and a hollow sphere, that mass is concentrated away from the axis of rotation. Where for a solid sphere, right, a lot of it is going to be concentrated evenly throughout the object. Okay, so that's going to be it for this video. So next thing we're going to do is we're going to put it all together and look at rotational dynamics in the next video, which is titled Rotational Dynamics.